Okay, so let's get started with lecture 15 here on op-amp applications. So for review, this is what we talked about on lecture 13. We talked about overshoot. Um, these are the kind of situations where you get to when your op-amp is getting very close to being unstable, but not quite stable. You can have this type of behavior where it looks like it's an underdamped type of system. So we talked about overshoot, how that could be measured by phase margin, and a different type of way of measuring phase margin like this. Phase margin also gain error, how those two things are related. What it looks like graphically in terms of the angle of the the feedback gain right here, and also the phase margin right there. That looks like graphically in terms of this unit circle. And also for the um, the first order, second order, and third order systems for this looking at stability, where this is t equals -1 in all these cases right here. And for the third order system, we see that this t equals -1 can overlap this lobe right here, and that's where you can get this instability. These two systems are stable, actually. So for lecture 14, we looked at cascaded macro modeling, where we're looking at a cascade of op-amps, amplifiers, and then we put them in terms of these macro models right here. And if we look at them in terms of their resistances seen on their inputs and outputs, we can get that from their voltage division. But if we make this approximation where the output resistance, this R out, is very small and negligible, then we can take this factor as being nearly 1. And so our output is just in terms of these factors of the gains of each of the op-amps, each of the amplifiers multiplied by your VS, which is where you're starting from. For active filter, we looked at low pass. Today we'll look at high pass and also band pass and compare them to the low pass. But we start off with the low pass right here. This is the feature that we're looking for, where Q is around 0.71, which is like 1 over square root of 2. But it does have some peaking right here that can happen, and sometimes you might want to avoid that. Here's the frequency response of a cascade of these, and for each one you're adding on, you're getting another -20 decibels per decade. So the slope gets higher order for that, so you get an improved response. And we also looked at an instrument amplifier. Okay, so the new concepts for today, we're going to continue on with active filters. Then we're going to get into switch capacitor circuits, and then we'll answer some last questions about the exam, our practice exam, before the exam on Friday. Okay, so high pass filter with gain. So just to remind you, this is what the low pass filter looked like. Here are a couple of the block symbols, and in this one, you can see like the lowest type of wave is able to get through, and these are crossed out. So there's like a low pass symbol. Here's a high pass symbol where the high frequency gets through, but the mid and the lower ones do not, or it looks like that. The difference between the two, for the low pass, you have a capacitor right here. This replaced with a resistor here, and these two resistors are replaced with capacitors, and this capacitor is replaced with a resistor. On this, you do have this piece right here, and this piece looks like a non-inverting op-amp, at least just this piece right here. And that one is just like a follower type of thing for that side. Now here is how you can compare their gains. So the gain for the low pass looks like this. The gain for the high pass is like this right here. And you can see the differences between the cutoff frequencies and also the quality factors. So the cutoff frequencies are the same. There's a difference in the quality factors of the two. Okay. And this is, K's right here is a factor. It's on this resistor right here, assuming that that's, tunable. Here's what the frequency responses look like. So for the low pass, you have these frequencies they're able to get through. And for the high pass, these frequencies are able to get through. Now you may have some peaking on both of these right here, but that depends on your quality. For these right here, on both cases, that's where your Q is 0.71 on both of these right here. Okay, this is where it's below 0.71, you get peaking if it's above 0.71 on both cases. So for their band pass, you could think of that as like combining both the low pass and the high pass together. The amplifier looks like this right here. Here's a symbol of that, where the middle frequency is able to pass through, and the upper and lower frequencies are not able to pass through. That's also the symbol. And here's the gain, frequency, and quality. This RTH right here is given by this expression. And for RTH, what that really is you can like convert this into like its Thevenin equivalent and just combine this into like one type of resistor. And that's why for this right here, it looks, you only have like R1, R3, R1, and R3 for both of that. And you can just plug that into both of those. Otherwise, you just take this and then actually just stick it in there. Okay, so for sensitivity, at times it is important to, when you're designing these types of systems, to look at the sensitivity of these type of filters. And you're concerned primarily with the sensitivity of your frequency and your quality factor to changes in some element values. Okay, so basically sensitivity is it's a change of one parameter with respect to the change of another, like a ratio. So whatever your parameter P is with respect to whatever your parameter Z is. Okay. In terms of magnitude and frequency scaling, this is important because what you can do is you could change the magnitude of your amplifier or its frequency without affecting other things. So what it says here, the values of resistance and capacitance calculated for a given filter design may not always be convenient, or the values may not always correspond closely to the standard values that are available. So this magnitude scaling, it can be used to transform the values of impedance of a filter without changing its frequency response. And for frequency scaling, it allows you to transform the value of the frequency to another value without changing the quality. Okay, so how this happens for magnitude scaling, what you basically do is you want to scale all your resistors in your circuit by a factor of this Km for magnitude, and you want to scale all of your capacitors by, you want to divide that by the same stiffness. I mean, not stiffness, this Km value right here. And so this is what happens to your impedance, right? It gets increased by that factor of Km. But your frequencies that you're getting by taking all of your resistors and placing this Km in front of that, and your capacitors, you're dividing by that Km, they cancel out, and so your frequency remains the same. And same for your quality factor. You're dividing all your capacitances by Km, multiplying all of your resistances by Km, and they have no effect on the Q. But you do change the impedance by that value. So that's magnitude scaling. For frequency scaling, what you do, you leave your resistors alone, and you only change your capacitances. So you divide all of your capacitances by this value Kf. Okay, and so what that will do, it won't have any effect on your quality factor, right? By dividing by all of your capacitances by K, no effect on your quality. But for your frequency, it will scale by that value. Okay, so you can play around with your value for your magnitude and your frequency by doing that type of thing. You may even want to use both. Okay, so switch capacitors are kind of interesting because what they allow you to do is to eliminate the need for resistors. Okay, I mean we've seen this idea before where on the last lecture we talked about eliminating the need for inductors. Now we're doing the same thing for resistors. So, and of course the reason why is because these resistors, they also occupy a large amount of area when compared to the size of transistors. So switch capacitors, they're a way to eliminate resistors in filters. This is done by replacing the resistors with capacitors and switches. The filters become the discrete time or sample data equivalents of the continuous time filter. And these resistors of the continuous time integrator is just replaced by capacitor and MOSFET switches, S1 and S2. I'll show you an image next. So the switches are driven by a two-phase, non-overlapping clock. And it has two phases, phi1 and phi2. So when phase phi1 is high, the switch S1 is on and switch 2 is off. And when phase phi2 is high, then switch S2 is on and S1 is off. So here's what you do first. So this is just a simple integrator type of system right here. You take your resistor and you replace it with these two switches. And you have this capacitor. And so what's happening is that these switches are, when this was on, that one's off. When that one's on, this is off. And so what it allows it to do is this switch allows this capacitor to charge up while that's off, and that's remaining unchanged. And then when this is off, this is on. This allows it to discharge and affect this capacitor over there. So another image of what's happening is like right here with the phases. Okay, so when this phase is high, this phase is low, right? And it's not completely overlapped. There's a slight offset, okay, between the two. So the switching doesn't happen exactly at the same time. But when this is low, that's high. So it's either charging or discharging one at a time. And they're just passing back and forth between the capacitors. So one way to think about it is like this. There's no charge going this direction into the op amp, right? But the charge that's on this plate, it's basically going back and forth between this plate and this plate as it does its thing. So another way of looking at it for phase one, this switch is closed, so charge is able to build up on this capacitor, okay? Nothing's happening over here because the switch is off, and so whatever charge is on there just stays on there, okay? And then on phase two, what happens is that this switch is off, but this switch is on, and then charge is able to flow between these two capacitor plates right there. And of course, the direction of flow depends on the positive sets of current flow. But what's really nice about that is even though you're changing things by having current flow back and forth between the two capacitors, the overall result at V out is in effect the same as having a resistor there. And one way to think about it is like this. So for phase one, the charge on this capacitor right here is going to be the capacitance times the voltage, right? And then for phase two, the charge in this capacitor is going to be that capacitance times the voltage, okay? There's a sign difference because of the direction of flow. But if you equate the two charges together, okay, because charge for one is offloading to the other, then you get this expression right here. And this looks a whole lot like, an inverting amplifier, right? Where it's negative, and instead of having, the feedback resistance over the input resistance, you have this ratio. So here's the output multiplied by negative of this ratio of that input.
How do you equate those two? It's deltas, and you can't equate the charge of two capacitors since it's not going to be the same if they have different capacitance values. There's no way to set those equations equal to each other.
Yeah, well, yeah. So the thing is that they have different voltages because of the capacitance, but the charge of one is being dumped onto the other, right? So even if they have two different charges, even if they have two different capacitances, that just tells you how much voltage is on there at that time. You see what I mean?
You still can't equate those because they don't both have charges in that. One has a delta charge. Actually, that was my question. Why
Uh,
is there a change in voltage, change in charge? What is that for?
why is there a change in voltage?
Yeah, why is it a delta V out rather than just V out?
Well, are you talking about right here?
Yeah. If
Oh,
I say you equate those two, assuming the charge is conserved, that Q1 is just the same as Q2, but I don't understand why you got it written as delta Q, delta V out.
um, well, I guess what you can think of it as is okay. So I guess one thing to think about is that as you're moving in time, you're having more current pass through this amplifier going out, and so it's sort of like accumulating in time. So so what's happening is that this voltage that's coming out, you could think of it as the voltage at some value how do I write this? So these are like this period of time right here. So at each step in time, your charge that's being built up on this capacitor is then being passed through, and so you're seeing this voltage that's being changed in time.
Okay, so it's just indicating that it's not like instantaneous from 0 to V out.
Oh no,
Okay.
yeah. Um, and it's best to think of it as like you're sampling, in time, right? Um, and another way to think about it is in terms of resistance. So if you look at this Q right here, which is like your current multiplied by your period of time, and this current right here is V out over R, and you're stating this equal to C1, then if you solve for R, it's like this period of time over your capacitance, and that's your frequency, where this FC is your clock frequency. And for an example, the book gives this. So if you have this capacitor that's like 1 picofarad, and your switching frequency is 100 kilohertz, the equivalent resistance is 10 mega ohms, and that's actually quite hard to achieve with like with a regular type of resistor today, and with the finite space you have. So you're able to achieve much higher resistances like this. Okay. But anyways, that's the purpose of switch capacitors, doing it that way. Okay, so are there any questions about switch capacitors or the topic of band pass or high pass before we start looking at the exam material? Okay, so let me put this up. Yeah, so even though we went over the material over the weekend, you guys may have some remaining questions after like looking it over. Um, okay, so in terms of question one, anyone have any questions about decibels? Anything on question number one? About converting the gain to decibels, or huh? Do we do what? Oh, power gain. Oh, so what's your question? Oh, yeah, yeah. So so the difference between the two. So if you're given like the voltage gain V out over Vn, and you want to convert that to decibels, then you're going to use 20 log V out over Vn, right? Or the same thing with current. Current out over current in is going to be 20 log if you're going to convert that to decibels. This is in decibels. But if you have power, if you're looking at your gain in power, then you're going to do your 10 log P out over Pn, right? And of course, the reason why is because this 10 here is because power is in terms of your of square root of your signal. Okay, so you could think of this as having the squared in here. You could pull it out here in front and it'll be 20, but having in there, then you're doing power ratios. So, and this is just in general for any kind of signal. You want to, when you think about it in terms of power, it's like a signal that you're squaring, right? Even though unit-wise it may not be in terms of watts, it's still like a squared signal, and that's why you're having the 10 out there in front instead of 20. Yeah, and also this, when you are looking at the cutoff frequency, 3 decibels down for a system like this or this is very different than 3 decibels down for a system like this. If you go 3 decibels down for power, that's cutting down this ratio in half. I mean, it's cutting down the output in half, going from input to output. But for 3 decibels down for the voltage or input, that's going down by a factor of square root of 2. Okay. Okay, what else? So anything about so anything else about question number 1? Okay, let's move on to question number 2. What about this? Guys are okay with this right here? On this one, you're looking at the voltage gain, power gained of the amplifier, power being delivered to the resistor. One thing to be careful about, I was looking at the book in sometimes you have to think about exactly what is the output and input. And so for this output and input has to do with the amplifier and not this source right here, because that's going to change things. Okay, so sometimes it's clear, sometimes it's not, but how we're looking at it is that we're looking at with respect to the amplifier and not the source for the input. Okay, so what about this question on number 3? This has to do with looking at the voltage transfer characteristic. Yeah, sure. So on this problem right here, you have, where's my little pointer? So you have a signal coming in that has a DC offset and has this type of amplitude. So sinusoidal signal coming in at this frequency. Now we know that the output's going to be at this frequency, but it may be a phase shift, right? Now for input, if you want to use this plot, one convenient way to do it is look at the input coming in this direction, and the output, coming over in that direction. That sort of helps you determine if there's going to be any type of cutoff. So one way to do that is to have it like this. Right? And so this voltage right here, so it's at 3, and then you're going to go plus and minus 3. So here's 0, 1, 2, 3, right? And it's going to go up 3 right here, and that is cut off. That's being cut off right here. And then down 3, it's okay. So we're looking at something that looks sort of like this. So this piece right here, that's at it's like I don't know, 4.5 or whatever. So basically, you're at 3, and it's going to go high as 6, and then low as 0, right? So your signal coming in looks like this. But this piece coming off like that, it's going to be sort of like that, coming off of that, where it's being clipped. See that? It's clipped here, but below that goes through unscathed. So if you look at this value 3 coming in, has an output of this voltage, and so that voltage right here is at 7. Okay, so then you can start writing, what that's going to be. So it's going to be 7 plus, and then you see from right here at 0, that looks like, I don't know, around 2.5 right here. Right, so if that's 7, it's going to go down like 2.5, and then so if it goes down 2.5, we're talking like 4.5 of amplitude. It's going to try to go up 2.5. I mean that amount too, but it's going to be clipped, right? So we have the same frequency, which is 120 plus some phase. So, and then it can only go as high as 9 volts right here. So that's the max it can go. So this, if the voltage is less than 9, and this, if the voltage is greater than 9 volts, then it's 9. So this is like the output voltage right here. So I think 7 is clear. Do you see how this 4.5 is obtained? What was that? Oh, yeah. So yeah, exactly. So so remember, it's centered at 3, and it's going to go as high as 6, but that's going to be clipped at 9 volts. But then it's going to go as low as this right here. But on the output, it corresponds to a 2.5. You know, I'm like eyeballing it, right? Around 2.5 coming out. So if it's at 7 and then goes down to 2.5 from 7, that's like a change, right, of that amplitude. But it's also going to try to go as high as 2.5. I mean, that change higher as well. So that's going to be the amplitude of the oscillation. Yeah. That's another way to do it. Yeah, exactly. Yeah, exactly. If you guys want to do it by slope, where you look at the rise over run, that's valid too. I'm not sure exactly which way is easier, but whatever you're most comfortable with. Now, doing it with a slope, yeah, okay, that's cool. But also make sure you get your DC right as well. So anything else with cutoff? All right. For number 4, what's the gain of the amplifier in terms of the resistors only? That's basically, you know, you do your KCL here, KCL there, and then you do your ratio of your output over input. And here you're treating this as an ideal amplifier, unless it says otherwise. For number 5, as many of you have said, this is this is the summer, right? And so it's giving you the values of these right here. So this right here is an inverting amplifier, where the output contribution from each one of these is just the feedback over the input resistance. Contribution from this is feedback over the input. Then you're multiplying that by the input. That's what you're getting here. This right here is just multiplying all that by -1, because these two resistors are the same value. Now, hopefully, when you guys see something like this, you can immediately jump to what the gain is, right? Hopefully you've seen this enough times. Just because if you have to do KCL every single time, it's going to slow you down. So it's really good to be able to recognize something like this and say, oh, I know what that is. That's an inverting amplifier, and I know what the gain is just based on the feedback and input resistance. Same here, another inverting gain type of scenario. So for number 6, this right here, so you're given this expression, and this is like a bandpass. Well, one of the forms of a bandpass, right? And then you're asked to find these values right here. Okay, so now in this case, yeah, so because we saw a bandpass today, and we saw what that looked like, and that was, that was, let me see this one. Yes. So, so see this right here. Here's the form of this bandpass right there. And even though the denominator is the same, you know, it has this factor, but right here it has that that s omega 0. So there are different forms of bandpass. For this one right here, what we're looking at is this form where we have s squared plus omega 0 over q s plus omega squared, and on top we just have omega over q. Oh yeah, well I guess you do have this. You can have this factor in front too. Yes. Yeah. So what you want to do in this situation is put it into this form, and you do it by first identifying what omega squared is. Right? Oh wait, I'm sorry. First you get rid of the factor in front of the s squared. Okay, that's number one. So I guess we can label this. So number one, get rid of that. Number two, identify this omega. That's step number two. Go divide out. Step three is identify q by this factor that's left in front of the s, because once you identified omega, you could plug it here and then determine what q must be in order to get this factor, right? So this is step three, identifying your q. Once you have your omega and your q, then you can factor that out of that top numerator to find out what your a is, or your k, your multiplication factor. Okay, yeah.
Will we just need to memorize that form, or would we be given that form on the test?
Yeah, that's a good question. How do you guys feel about that? Are you guys familiar with this enough, or should stuff like this be given to you guys?
Personally, I said like it, but I don't know what everybody else knows. If it was on there, because I don't have that memorized.
Okay. Okay, yeah. No problem. I think this is the only kind of problem that you may need something like that on, but let me know if there's another. So this right here is basic feedback, right? And on this, you want to determine the overall gain, right? And so yeah, so for this gain right here, you want to look at the output over the input, and so what you want to do is determine what all the voltages are, and so what's VO going to be? Yeah, it's going to be A times this VD, and what VD is basically this VI minus VF, right? What VF is going to be your V out times this beta, and so you're going to have all your equations of your voltage relationships, and then what you do is you just have to substitute them into each other and get it in terms of V out over Vn. You guys okay with that? Cool. Okay, and what about something like this, where you have to determine the transfer function given a plot? Any questions about that? You guys all good with that? Okay, and I'm not sure if I'm going to have a Blackman's theorem type of problem on there. And the only reason why is because if you think about it, this problem is really like almost like three kind of problems in one. You have to determine this, that, and that. You know, it's I mean, it's not too complicated, but I'm just not sure about that yet. If we did have a Blackman's theorem problem, would you guys be okay with that type of problem? Are you guys comfortable with Blackman's theorem? Yeah. Yeah. Wait, do you mean like the input or the output one? Because on this you have to like determine both, right? The short and for at least for T.
I mean, like, would you be more prone to one with the open circuit being 0 or the short circuit being 0?
Oh. Oh, I see what you mean. I don't know. Is there a significant difference to you in those? Yeah? Yeah, and I'm just still on the fence if we're going to have that type of problem on the exam anyway, just because it is kind of long. I mean, I have more than enough other problems to choose from. Huh? Oh, yeah, 10 basic questions and 2 extra. Yeah. And so what about something like this, where you have to just determine like the power delivered? So what's kind of complicated here, because this is a non-ideal amplifier, okay? I think that's the biggest problem here. So it's a non-ideal amplifier. Okay, so you do have to consider the voltage across here, where that's not equal to that. And you also have to be able to identify the value of or the gain in voltage right here going through that amplifier. Right? Any questions about that one? Okay. Oh yeah, and be very careful about your signs. See how these things are like switched around sometimes? Be very careful about the signs as you're going around your paths. Last couple of things. So this one right here, this is just a lot of voltage division right here. And you guys have to understand like the common mode rejection and the common mode input. And for the last thing right here, I don't know, this may be too simple for a bonus, maybe. I don't know. Maybe this could be like a regular type of question instead of a bonus.
This would be another one like the previous one where it's like either you know the power or you don't. So if it was provided, that would make it a lot easier. Or if we had a method,
Yeah.
I don't know.
Yeah, yeah,
So I prefer if you put it down, but
yeah. Okay, guys, so all right, that's it for the exam review again. So I'll see you guys on Friday.